So now we understand the diffusion model. We want to move on to something called the SIS model. Now the SIS model looks pretty much exactly the same as the diffusion model, except for now we allow for the possibility that after someone's become infected, they can move back into the susceptible pool. So they can become recovered in a sense, but then they're also susceptible again. So this would be for something like the flu, where after you're cured of the flu mutates and you can become infected again. It wouldn't work for something like measles, where once you've had the measles, you're no longer going to get the measles. So here's how the model looks. It looks exactly like our model looked before. There's some number of people that have it at time t plus 1, and that's the number that have it at time t, right, plus the new people who get it, right? And this depends on somebody who has it meeting somebody who doesn't have it, right? And this is the transmission rate, and this is just the number of contacts. But all we do to this is we subtract off this minus AWT. Well, what is this? These are the people who become cured, right, who no longer have the disease, and they're going to go back into this pile N. They're going to be people who could get the disease anew. So all we're doing is sort of like throwing in a rate of people sort of getting better. Well, now here's where this model is sort of more interesting, because in the diffusion model, something just spreads, right? It starts out slow, it goes fast, then it tails off. But here, what happens is while people are getting sick, at some other rate, some rate A, they're getting better. And if people get better faster than people get sick, then what's going to happen? The disease isn't going to spread. So this model is going to produce a tipping point. So let's simplify things a little bit. If we rearrange terms, what we get is an equation that looks like this. Now, how did I get this equation? All I did was I pulled this WT term out, right? And I crossed out some n's. So let me show you how that works, right? So up here I've got, let's just focus on this part. I've got NC tau, right, times W over N, times N minus W over N, right, minus AW, okay? And so what I do is I say, well, you know what, let's cross out this N with this N. That's fine, because those N's go away. And then I've got a W here and a W here. So I'm going to pull out that W, and then I've got C tau, N minus W over N minus A, right? That's what I've got. And if I look over here, that's what I've got. I've got C tau, N minus W over N minus A. So this is just a simplification. So when you write models, it's useful to be good at algebra. If you can do lots of algebra, you can simplify things. Well, why do we want to simplify things? Well, here's why. Look, suppose we're early on in the disease. So that means WT is really small. So that means that N minus WT over N is going to be really close to 1, because basically a very small percentage of the people in the population have the disease. So now if I look at this thing, I can say, well, you know, WT plus 1 is really equal to WT. WT plus 1 is equal to WT plus WT times C tau minus A. So this thing is going to spread if C tau minus A is positive, and it's not going to spread if C tau minus A is negative. So this is going to come down to, is C tau minus A bigger than 0, right? Or is C tau bigger than A? Or another way to write this is C tau over A bigger than 1, right? And this leads to what's called the basic reproduction number. We let R0 equal C tau divided by A. If C tau divided by A is bigger than 1, the disease spreads, right? Because that means that WT plus 1 equals WT plus something positive, right? If R0 is less than 1, right? In other words, if CT over A is less than 1, then WT plus 1 equals WT plus something negative, and the disease dies off. So this R0 is called the basic reproduction number, and what it basically tells you is, does the disease spread? But notice here we've got a tip, right? R0 less than 1, no disease spread. R0 bigger than 1, disease spreads. So let's take some real diseases. Diseases like measles, mumps, the flu. The R0s are 15, 5, and 3. That's why these are real diseases. There might be a ton of diseases out there that have R0s less than 1, and we never even hear about them. Why? Because they don't spread. Now again, for things like measles and the mumps, once you get them, you don't fall back in the population. So there's a model that you use there called the SIR model, which is very similar to the SIS model. But for the flu, right, you fall back into the pool, so you can think of it like this SIS model. Now what's interesting here is, right, from these basic reproduction numbers, we can say, you know, they're past the tipping point, the disease is going to spread. But let's think about this figure. Why do we construct models? Well, bunch of reasons, right? But one reason is to design policies. You could say, how do we stop these things from spreading? Well, one obvious answer is vaccines. Then the question is, how many people do you have to vaccine? Well, turns out the model will tell us. So let's think about it this way, right? Let V be the percentage of people that you vaccinate. So there's this basic reproduction number, R0. That's sort of like the rate at which things spread through the population. Well, if I vaccinate some percentage of the population, that's just going to reduce, right, the basic reproduction number by that fraction. So if half the people were vaccinated, R0 is effectively divided by 2, right? And if 75% of the people are vaccinated, R0 is going to be divided, in effect, by 4, right? Because you've only got 1/4 of the real population. So the question is, how many people do we have to vaccinate as a function of R0? Well, in some sense, if we vaccinate, right, V people, it's like we've got a new R0, right, little r0, which is just the big R0 times the percentage of people in the population that aren't vaccinated. So what we can do is we can say we want R0, big R0, times 1 minus V to equal 1. Actually, we want it to be less than 1, right? Well, we can multiply this out. We get R0 minus R0V, right, has got to be less than 1, right? So we can bring this over to the other side and we get R0 minus 1. We need to be less than R0 times V. So that means we need V to be bigger than 1 minus 1 over R0, right? So what we get is we get this equation that says this is how many people we need to vaccinate. Well, let's go back. Remember, the measles were 15, the mumps were 5. How many people do we need to vaccinate to prevent the measles from spreading? Well, that's just 1 minus 1 over 15, which equals 14/15. So we need to vaccinate 14/15 of the population against measles if we want the measles not to spread. For the mumps, right, we need 1 over 1/5, right? We only need to vaccinate 80% of the population. Well, here's where the model is so useful. Again, this model isn't exactly right. We're leaving out all sorts of things like networks and changes in contact structures in different locations and stuff like that. But still, what this tells us is, which is really important, is depending on how virulent the disease is, you have to change how many people you vaccinate in a pretty, understandable way. Now, the other interesting thing is there's a tipping point in terms of vaccines, right? If we vaccinate 75% of the people and we needed to vaccinate 80% of the people, well, guess what? It's not going to work. The 25% who don't get vaccinated are all going to get the disease. But if we'd have vaccinated 81% of the people, then the 19% of the people who don't get vaccinated, they're still going to be protected because the disease isn't going to spread. Okay? So the cool thing about this model is it's given us a tipping point, R0. It's also given us a policy. And this policy is interesting in the sense that, it's of no effect. Really, vaccination has no effect, really, other than the people you vaccinate. Right? It has no population level effect until you get to the threshold. Once you pass the threshold, then that next person to get vaccinated, in a sense, right, makes the whole rest of the society immune because the disease can't spread. So step back a second. In the diffusion model, right, where we got that nice sort of S-shaped curve, there's no tip. In the SIS model, there's this R0, which is the tipping point, right? So there's this value 1. So there's no disease if R0 is less than 1, and there's a disease if R0 is bigger than 1. What you can do by vaccinating people is, in effect, reduce R0. So that's the SIS model. We've talked about it in the context of disease. You can even think of it, though, in terms of the spread of information, as we talked about. And it's a really interesting model in the sense that it does also generate a tipping point. It's another nonlinear model, and it's a model where we get this, threshold phenomenon. Less than R0, R0 less than 1, no spread.